with response quantities indicated as B1 through B4. Now, here is a slab of a parking garage that we tested. As you can see, there's a little bit of, this is the second shot, and we marked the cracks. It deflected, it bounced back. There's no permanent deformation, which means there's no yielding. This is okay. You can continue using the building. It could either be immediate occupancy or it could even be operational because damage is superficial. So these are, in physical sense, how do these damages correlate with response quantities and how do they correlate with visible damage? Okay, so these are the verbal descriptions. If it's hazardous, the component is likely to fail, produce debris. Heavy damage is it's unlikely to fail, but it's not usable. Moderate is it may be repaired. Superficial is it could be used without even repair. Now, in order to see if your elements fulfill the code requirements, it's not enough to just analyze one column. We have to do primary members, secondary members, and non-structural components, right? So if you have, let's say, your owner said, I want life safety, okay? And I don't want anybody to be killed, then you have to design it for low level of protection. Your primary members should be moderate, which means B2. Your displacements has to be less than B2. Your secondary components can be heavy, it could go up to B3, and then non-structural could be heavy as well. So you have to look at those three combinations to decide. And for operational, everything has to be superficial because people need not leave the building. So you essentially apply this to structural and non-structural members. Now, one other very, very, very important design concept and design tools is PI diagrams. When we design reinforced concrete columns, we have column interaction charts, right? PM, so with design moment and design axial load, we come and make sure that it's inside the curve that indicates it's safe. Similarly, there are PI diagrams generated for different members. Let's say this PI diagram is generated for a column. So this is the pressure and this is the impulse. So given my pressure and impulse, if the intersection lies inside the superficial damage, that's great, nothing will happen. If it lies here, I will get moderate damage. If it lies here, heavy damage, and so on. So if you have PI diagrams available, if you're in the business of designing buildings for blast, you will have a whole bunch of PI diagrams available. Once again, my PhD student developed RC Blast, which is a freeware, and it's quite extensively used to develop PI diagrams. But you just like column interaction diagrams, you need to have pages and pages of PI diagrams. If you don't want to do any calculation, just enter with pressure and impulse. Impulse is the area under the curve. Wherever it falls, the intersection, then performance level is accordingly. You can even go one step further. You talk about charge weight and standoff distance. These diagrams are not used that frequently because there's extra work. Instead of pressure and impulse, you work with a charge weight and standoff distance that produces that pressure and impulse. And once again, if you have, let's say, 150 kilograms of bomb, which is at, let's say, 3 meters, and it's hazardous failure, right? If it goes up to, say, 10 meters, 30 feet, it's on the border of heavy damage and moderate. So these charts are also available, or you can develop them if you use them very frequently. I also would like to talk about glazing hazard, because this is the single most important thing in glass, because first thing that comes down is windows. And windows are, of course, made out of glass. Glass is very brittle. If they break, it flies in, shark-like shark objects, and how do we quantify security of glass window is the next question, okay? So once again, for different performance levels, there are ratings of glass window. Low hazard rating, very low, minimum hazard. How do they talk about rating levels? There are GSA standard tests that qualifies windows. GSA, once again, is General Services Administration. This is U.S. government agency that looks after government infrastructure. They have a test. So this test involves applying either 4 psi or 10 psi pressure on a window, and if fragments fall within 1 meter, it is very low hazard or high protection window. If it goes all the way fragments to 3 meters, then it is low to medium. If it goes past this 3-meter distance, and this is a witness panel, it's a styrofoam wall, and those glass fragments go and get stuck on the styrofoam, and you have to weigh them. There's a procedure. It's level 4, and then level 5 is different hazard. So depending on the projectiles, how far glass fragments go, windows are quantified for certain performance levels. This is our laboratory where we do tests for to quantify windows, and this is a styrofoam witness panel, and we have a little window behind which there's a camera. This is our shock tube, which is a blast simulator, and I'll talk about details after the coffee break. And here is a window test, okay? In fact, this test was glass-resistant window shades. The Canadian ambassador in London, England, had a residence immediately across the U.S. Embassy. The ambassador said, I have a 14-year-old daughter, I'm not going to live in here unless you do something. So they decided to put blast-resistant shades. So the moment blast pressure hits, shades will close. So these have steel pieces inside, very strong, and they asked us to verify that. In fact, Canadian Parliament wanted to buy them. This was a British-made product, and things didn't work. You can see bits and pieces of glass, and at the time we had a wood frame. Wood started coming in, so it didn't meet Canadian standards, and they ended up not buying it. The supplier was upset with me, but that was the results. So this is the witness panel. You can see all the glass fragments marked, and we subsequently weigh them, and depending on GSA, if it's greater than so much weight, then it qualified as hazardous glass. So it needed to be glazed with film, security film, okay? And similarly, doors have different standards and different performance levels. For example, if it's high level of protection door, it has to be operable after the event. After the blast, you should be able to open the door and leave. But if it's low level of protection, so long as you can push it open, the mechanism need not work. So there are different levels specified in ASTM F2247. There's another standard. Once again, we did blast-resistant door tests, and this is our lab, instrumented, and we applied different pressures. In this case, door performed extremely well, for example, but there are situations where the handle and the other mechanical parts did not function as well. So once you meet these performance levels from the analysis side, now the last step in completing design is to do structural design and detailing. And load combinations used are dead load plus half of live load. In Canada, we have snow load, quarter of snow load. Blast load is not increased because it's a rare event, just like in seismic events, we don't increase earthquake loads. It's already, increase is already built in, or the risk associated with